In this section, we're going to look at the gas laws. The gas laws are a group of mathematical equations that show the relationship between pressure, volume, and temperature. As you can see, there's four of them we're going to look at. Now, we specifically aren't going to measure or calculate the amount of gas, the moles or the mass. That'll come a little bit later. So again, just focusing on three specific measurement properties of gases: the pressure, the volume, and temperature. In all four of these, we can create different scenarios, whether we're using a balloon, an aerosol can, some type of container that can show the relationship between these different variables. What we're going to do is we're going to start off just looking at two of these variables at a time. So just pressure and volume, then just volume and temperature, then pressure and temperature, and then finally all three. So what's going to happen in these first three, one of the variables is going to be constant, meaning it's not going to change. So we can only focus on two at a time, which will make things a little bit easier as we introduce these. So the very first one, Boyle's law. Boyle's law simply is explaining the relationship between the pressure of a gas and the volume of space that the gas takes up. And we're going to look at this relationship assuming the temperature of the gas stays constant. Now, the whole concept of Boyle's law says pressure and volume are inversely proportional. Let's think about that. Best example is taking a balloon. You take a balloon, you blow it up, you tie it off. You take that balloon and you squeeze it into a smaller space. So what are we going to do? We're going to make the volume of that balloon smaller. So you make the volume of that balloon smaller, the pressure goes up. So much so that if we make it small enough, the pressure is going to get so big, the balloon bursts. Now, let's just say we take that balloon and we don't squeeze enough that it breaks, but we then let it expand to its original size. We increase the volume. Then what happens to the pressure? It goes back down. So this is what we call an inversely proportional relationship. As pressure goes up, volume goes down. As volume goes up, pressure goes down. Sometimes it's a little bit easier to explain in terms of one of the measurements and how that affects the other. Now, mathematically, here's what it is. We have this simple relationship. Pressure times volume equals K. Now, what that means is whatever the value of P is and whatever the value of V is, if one goes up, the other has to go down equally so that the product of those two measurements is a constant number. It does not change. Now, what is that number? It depends on a whole lot of other circumstances. Okay? But it's simply if one goes up a certain amount, the other has to go down an equal amount. Now, when we say equal amount, we got to explain a little bit more what that means. We're not saying, well, if one goes up 10, the other one has to go down 10. We're talking more things like if something goes up by a factor of 2, then the other thing has to go down by a factor of 2. If something gets tripled, then the other thing is going to decrease by a factor of 3 or decrease by 1/3. Okay? That's what we mean by proportional, and then more specifically inversely proportional. Now, how do we actually look at a calculation in terms of if we're trying to solve a situation? Here's the equation that we're going to look at. Simply says P1 times V1 equals P2 times V2. Now the subscript 1's just talk about the initial conditions of the pressure and volume of the gas. Subscript 2's talk about some final condition. If you're in physics, sometimes we use 1's and 2's or 1's and 0's, initial, final. We're just talking about one set of conditions and then the conditions change. So what's going to happen is you're going to be given 3 of these 4 conditions, and you're going to be asked to solve for the 4th condition. Now, the only thing that must be true when you do this calculation is the units must be equal. That means both pressure units must be the same. ATMs, millimeters, torr, whatever. Both volume measurements have to be the same. Milliliters, liters, cubic centimeters, whatever the case may be. And that's simple. That's it. You notice here that mathematically, it's not if one goes up 5, the other goes down 5. Okay, we're talking about factors. If one triples, the other is decreased by 1/3, and things like that. So you'll see these as we go through. The first thing they have on page 370 is they have sample problem C. Okay? So you should be able to look through that and kind of see what they're doing in that particular problem. They give you a set of conditions, and they set up the problem, show you what to do, and you're able to follow through and solve for that. And again, it's a pretty simple calculation. You just plug in the numbers. Again, they're going to give you 3 of the 4 variables. You plug in the 3, solve for the 4th. That's your x. Okay? Now, what I want you to do then for Boyle's law is I want you to, the show me for this section is practice problem number 1 on the bottom of page 370. Okay? Again, pay attention to the question in terms of what units. Maybe they want the units or the answer to be in a certain unit. So make sure that you're paying attention to that. Next one, we're going to look at Charles' law. Charles' law is going to look at the relationship between volume and temperature. At this point, we're going to have constant pressure. So if we think of volume and temperature, think about a balloon being able to expand or compress if the temperature of the air changes. Okay? So if you get a balloon, let's say you blow it up and you put it inside, and then you take that balloon and take it outside into a really, really cold air. What's going to happen is those air molecules are going to get colder. They're going to lose kinetic energy. If they lose kinetic energy, they're going to move around less. And if they move around less, okay, lower temperature, move around less, what's going to happen is the size of that balloon is going to shrink. Those molecules are going to move less and less and less, so they get closer together. You take that balloon, warm it back up, temperature goes up, those molecules move around more, they expand more, and that balloon size will expand. So what do we have here? We have volume and temperature are a directly proportional relationship. One goes up, the other goes up. One goes down, the other goes down. So mathematically, here's what it is. V divided by T equals K. As volume changes, temperature has to change accordingly so that K is a constant number. Again, we're not worried about the actual value of K. We're just saying, all right, if volume goes from this to that, temperature has to change accordingly. Now, how do we mathematically represent that? Simple equation is V1 divided by T1 equals V2 divided by T2. Same situation. You're given 3 of the 4 variables. You're going to be asked to solve for the 4th one. The units must be equal. Both temperatures have to be the same. Both volumes have to be the same. Now here's the new piece here. From this moment on, if you're actually doing the calculation, you must put the temperature units in Kelvin. We'll use 273.15 just to give us extra significant figures. A lot of times they just say 273. Okay? Now be careful. They still may give you the question, still may tell you a number in Celsius, or they may want the answer in Celsius, but you have to do the calculation in Kelvin. Okay, so question and answer could be Celsius. You got to do the calculation in Kelvin. All right, so looking at Charles' law here, page 372. Sample problem D. Again, they give you a set of conditions. They give you volumes and temperatures. They're wanting you to solve for the unknown variable, the unknown measurement. They give you one set of conditions, then something changes, and they want you to solve for the remaining variable. So you can see through that problem there. They set that up, they work through that, and you can see how they've solved for that. For these, I've got two that I want you to show me at some point, number 2 and number 3 on that page. Again, just different variations of volume and temperature calculations. Actually, I think I said 2 and 3 wrong. I meant 1 and 2. So mistake there. Ignore 2 and 3. Instead, do 1 and 2. All right. So moving on. Last one. Gay-Lussac's law. So again, all these laws are named after famous dead scientists. So here we're talking about the relationship between pressure and temperature. Now, the volume is going to be constant. Here's the good one. This is an aerosol can. So you imagine a spray can, paint spray can, a hairspray can, a pop can even, could be that. Take a pop can, throw it in the fire, temperature of the molecules inside go up, gas is trying to expand, it can't expand, pressure builds, eventually, kaboom, it explodes. So what has happened here? Well, the temperature inside that container increased. It's not allowed to expand, okay? Constant volume, it's not allowed to expand. So what happens? Pressure goes up to the point where the pressure then is able to exceed the integrity of the container walls. Now, you lower the temperature, then you lower the pressure of that gas, whatever is in that container. So what do we have here? We have another directly proportional relationship. As one goes up, the other goes up. As one goes down, the other goes down. So it's very similar to volume and temperature. Okay? So again, if we think P divided by T equals K, as pressure changes, temperature has to change equally so that K is a constant value. Okay? So it remains the same. So see your pattern developing here. All right, so pressure and temperature, directly proportional. So we have almost the identical calculation from the last one, Charles' law. P1 divided by T1 is equal to P2 divided by T2. Given 3 of the values, you're going to try and solve for the 4th one. And again, don't forget, units have got to be equal, and temperature values must be in Kelvin for the calculation. So on page 373, we have sample problem E, where they're looking at pressure and temperature calculations. Does it really matter what's 1 and 2? Well, again, depends on how they word the question. Usually 1 is the conditions before there's a change, and 2 refers to conditions after the change. So as you read that question, you actually might be solving for T1. And another way the question might be worded, you might be actually solving for T2. Just kind of depends. All right. All right. So then on these, the two show me's are number 2 and 3 in the practice problems. Okay. A little different comparison there that you can work through. Again, pay attention to the question. Whenever it's involving temperature, the calculation has to be in Kelvin, but the question or the answer, you have to always check, is it in Celsius or not? All right, so now we've kind of seen, we've talked about, go back here to the beginning, talked about pressure and volume, we've talked about volume and temperature, and we talked about pressure and temperature. We've kind of done them all 2 at a time, but there's got to be a way we can do all 3, and there is. So here's what we're going to look at. If we take the combined gas law, and here are these 3 equations. This was the first one, this was the second one, and this was the third one. Now, if you're in a math class, Algebra 1 or Algebra 2, say, okay, I have these 3 equations, and math teacher tells you, simplify these 3 equations into 1 equation. Well, what you can do here, the first step is you could say, well, P1 divided by T1 times V1 divided by T1. That's basically the left side of the equation. The right side could be P2 divided by T2 times V2 divided by T2. That mathematically is equivalent to these 3. Well, we can simplify it even more and say, well, P1 times V1 divided by T1. P2 times V2 divided by T2. What we have right here is the combined gas law. We now have 1 equation that represents all 3 variables. And I think, okay, why didn't I just go to this one first? Well, because it's a lot easier to explain just 2 at a time. One goes up, the other goes down. One goes up, the other goes down. One goes down, the other one goes down. One goes up, the other one goes down. One goes down, the other one goes up. So as we're looking at two at a time, we can understand mathematically what's happening. We just jump to this. We're not sure why we put P on top and T on the bottom, or V on top and T on the bottom. Here we now understand how we can get to this end result. So in the end, here's our equation. Now, do we need to memorize the other three laws? Actually, we don't. Because let's say we have a problem where they say it is constant volume. Guess what? We just can ignore this number. We can just ignore V1 and V2. What's our calculation? P divided by T equals P divided by T. Do it again. Well, what if they tell us it's constant temperature? Then we ignore it. What's our calculation? P times V equals P times V. So this really is the only equation that we have to know. Again, we had to get to this point, but from this point forward, this is really the only one we have to use. Okay? And you can simplify it as needed. Okay, so given that, page 375. Okay, we've got sample problem F. You should be able to look through and follow through and kind of take some notes on. And the two show me's I want you to do are practice problems 1 and 2. Okay, and again, be able to at some point in class show me those so that you know what you're doing. Last thing, these are just big reminders. Now, any volume. Here's what I'd say right now. Any volume, just put it in liters because we are going to have them in liters later. Is this a mistake if you leave it in milliliters right now? No, but later we will have to. Temperatures always have to be in Kelvin when we're doing calculations. Now, again, pay attention to it. Does the question tell you Celsius or Kelvin? And do they want the answer in Celsius or Kelvin? You got to look out for that. But to do the calculation, got to be in Kelvin. Pressure units, the only thing that you have to do is you got to make sure they're the same. You make them both ATMs, you make them both millimeters, you make them both kPa, whatever the case may be. And that's it. Okay? So we've looked at a couple quick ways here to relate pressure, volume, and temperature. What we're going to go to next is then dealing with those in a reaction situation.